A solid circular shaft is required to transmit 100 kilowatt while turning at 26 revolution per second. The allowable shearing stress is 100 megapascal. Find the required shaft diameter. Right. So this is the question that is given. Let us try to find the solution. Okay. Now the power transmitted is given as 100 kilowatt, right? And the turning speed is also given. So using this, I can find the torque that is transmitted, right? So we have the power transmitted by shaft. Just solve this. Yeah. Power transmitted by shaft P is equal to 2 pi n by 60, right? Now in this n is in rpm, but here n is given as a revolution per second, so this is equal to 2 pi n, sorry, it is 2 pi n t, so it will be 2 pi n into t, where n is in rps, revolution per second. Or from this I can find t. T is equal to, this will go on the other side as denominator, p by 2 pi n, right? Now let us substitute the values. See, p is in kilowatt, so you should put it in watts in this equation. So this will be 100 by 2 pi. Okay, so 100 into 10 raised to 3. So this is now kilowatt, and this is 2 pi n is 26. So the torque that you get from this expression will be in Newton meter. So let us find this. 100 into 10 raised to 3 by 2 by 5 by 26. So the torque transmitted is 612.13. 612.13 Newton meter, which is equal to 612. Let me take one more decimal. 34. 612.134 Newton mm, because I can directly find the shaft diameter in mm if I put it in Newton mm. So this is the torque that it can transfer. Now tau is given as 100 megapascal. So we have torque transmitted by shaft. I had the equation here, let me just copy that. So this is a solid shaft, so it is T is equal to pi d cube by 16 into tau, right? So now I have to just substitute the values in this, or what is my torque? Torque is this, so substitute this value, right? So pi d cube by 16, it remains as it is, into tau. I'll put it in a bracket. How much is tau? Tau is 100 megapascal. So 1 megapascal is 1 Newton per millimeter square. So you don't have to do any conversion. Or D is equal to the diameter that you get from this is in millimeter already, so no need to convert anything. 612,134 into 16 by 100 by 5. Okay, this is the value, and this is b cube. So I have to take cube root of this. So it will be 31.47, right? You don't have to round off or do anything. You just leave the answer here only. In third year, when you go for design of machine elements, we have design of shafts, right? In which case, this we will be using the design data handbook and obtaining the standard size of shaft, next size of shaft that is available as standard, right? Because shafts needs to be supported by bearings, and bearings are available in standard sizes, and the shaft sizes made available according to that. So we have to use standard size of shaft. For now, you can just leave it like this. Is there any questions in this? It's pretty simple solution, right? So it is for 6 marks. Okay, we'll take one more. See, this uh, equation, right? The torque, basically what you get from this equation. This is called as the strength of shaft, or the torque transmitted based on the strength of the shaft. Now, when the rigidity is considered, or when the angle of twist is considered, then it is called the shaft design or strength of shaft based on rigidity. So this question is based on both of this. Let us see this. Determine the maximum torque that can be applied to a hollow circular steel shaft of 100 millimeter outside diameter and 80 millimeter inside diameter without exceeding a shear stress of 60 megapascal or a twist of 0.5 degree per meter. Use G is equal to 83 GPa, gigapascal. So in this case, what you have to do is you have to find the torque based on strength, and you also have to find the torque transmitted based on rigidity. Whichever is less, we will be using that as the maximum torque, right? So let us start with this solution. uh, Maximum torque based on strength of shaft. Okay, so the maximum strength based on strength of the shaft is given by this. Sorry, it is a hollow shaft, so it will be this expression is given by T is equal to pi by 16 tau d raised to 4 minus d raised to 4 by d, right? So this is equal to, I'll just copy this again and substitute the values now. Pi by 16, the maximum shearing stress is 60 megapascal, so I will put tau as 60, and the outside diameter is 100 mm. So this capital D will be 100. This will also be 100, and this small d is 80 millimeter. 80, right? So this is equal to, let me calculate this. So I'm doing this first. 100 raised to 4 minus 80 raised to 4 is this much by 100 into 60 into 5 by 60. So I have put D in mm, right? And shear stress is in megapascal, that is Newton per millimeter square. So the torque that we have got here is in Newton mm. So I will keep it to one decimal place only, Newton millimeter. Excuse me. Right? So this is the maximum torque we can transmit without any shear failure of the shaft. Or I'll make this in Newton meter also. So we'll move by three decimals, so it will be 6955.48 or 49 Newton meter. Okay? So this is the maximum torque you can transmit. Now maximum torque based on rigidity. We have torsion equation. Now what is our torsion equation? This one, T by J is equal to C theta by L is equal to tau by R. So I need torque and I need to consider the twist in the shaft. So I will eliminate this last term in the torsion equation. T by J is equal to C theta by L, or T is equal to C theta into J by L, right? So this is the strength of shaft based on rigidity. Now before I substitute all the values, let me just put this in the required quantity. Now we have polar moment of inertia J is equal to pi by 32 into d raised to 4 minus d raised to 4. It is pi by 32 into d raised to 4. Now since it is hollow, it is pi by 32 d raised to 4 minus d raised to 4. Right? Now this is equal to I'll just copy this again and put here. Now this d is 100 and this d is 80. So I can just take this So this is equal to, let me calculate again. So 100 raised to 4 minus 80 raised to 4 is this much into 5 by 32, right? I'll just keep this as it is. Like this. This is mm raised to 4, so I'll keep it in one decimal, that is more than enough. Mm raised to 4, right? So J is found. See, the theta is the angle of twist, which is given as 0.5 degree per meter, right? So theta by L is directly given here as 0.5 degree per meter. We have to put this in radians, right? So it's not C theta, it is theta by L is equal to 0.5 degree per meter, right? So this is equal to I have to convert this degree into radians, right? Because in the equation we have to put it in radians. So how to do this? 0.5 into 5 by 180, right? So this is in radians now. Or I'll write it like this, right? So this is my theta by L. Now substitute all these values in this expression. We get T is equal to C into T. Okay, C we did not define. C is equal to, how much is C? 83 gigapascal. I need it in megapascal. So 83 into 10 raised to 3, right? So this will be in MPa. MPa is also Newton per mm square. So if I put in MPa, I will get all the things correctly. Now I have to put these values in this expression. C is this much. So this is equal to, C is, I'll put it in a bracket, 83 into 10 raised to 3. Theta by L is this much into, open another bracket, 0.5 pi by 180, and J is this value. So another bracket, and this is equal to, now let us calculate this. Okay, I have this, so I'll start from this side. This into 5 into 0.5 by 180 into 83,000. Okay, so this is the torque. I'll just keep one decimal, and this unit is Newton mm, or T is equal to, just shift 3 decimals, so it will be this much Newton meter. Now, how much is this? This is 7-digit figure, and here this is only 4-digit figure. So, which will be the maximum torque you can transmit? It will be the minimum of these two values, right? If you say this is the maximum torque you can transmit, then the shaft will fail by shear, right? So, therefore, the maximum can transmit is this many Newton meter based on strength of shaft, right? Rigidity, based on rigidity, the torque is more. I cannot use that value, right? If you get this as less than what you got from the uh, strength, right? This value, then we could have done that. But here, this value is very large as compared to this. Okay, so this is the solution to this.